early in the morning yet? Okay, cool. So now I want to introduce the next speaker. I already actually introduced him. So he's all the way from Amsterdam, Italian from Amsterdam. Welcome to South Africa. It's your first visit here, is that right?
In South Africa, absolutely,
yeah. So anyone want to take him around, show him some things?
Please
He's
do.
flying out on Sunday evening. And so Urban, you better... you got the guy here.
Yeah, I know. We're sorted.
Okay, cool. Okay, so let me go to your presentation and hand over.
By the way, is it better to use a microphone or yes? It is.
I think we have to just...
Right, that's all right. Because I tend to move my hands a lot, so that at some point the microphone will go in. So if the microphone goes away, please just give me a sign. You know, I'm Italian after all. All right. Well, thanks. First of all, thanks a lot, Irvine and Jacques, for having me here. It was quite a long flight to get here, but I'm really excited. And we are from Brain Creators. It's a startup in Amsterdam. We're working with mid and large companies, trying to help them leverage AI whenever they are not capable of doing that yet. And I'd like to start first of all telling you why I love AI so much. When I was a kid, my dad, whenever we had problems in the house, used to have a toolbox with all the tools, screwdrivers, hammers, all sorts of different things. And when I was very young, I was not allowed to get close to the toolbox. He would, whenever we had a problem, he would just take the toolbox out and look at what was wrong and try to fix it. And I would just look at him every time taking a different instrument and managing to fix stuff. And I grew up with this image of the fact that my dad was a superhero. I still is for me actually. And part of it was the fact that he was able to use his tools so well. And so I always wanted to grow up as an inventor or someone who could solve problems. Fast forward quite a long time, I'm very old. Eventually I realized that machine learning and software is this fantastic toolbox which helps to solve problems. And that's what we do all the time. And that's why it's so exciting. I find AI so exciting. So, what I'm going to talk about today is these 4 topics. I will start with an intro in deep learning, then talk about why I think AI can help in so many different fields. Talk a lot about data and how you can gather it. And before I start with the deep learning part, I like to see from you how much actually do you know about deep learning. So is anybody of you actually working already in deep learning using TensorFlow, Theano, Lasagna, Keras? You are? Okay, so for the one of you who do, of course this might be a little bit, again, rehearsed all things you already know, but I hope that you're going to get a different perspective on it. So that's the idea. So this image everybody knows. I think I've seen it in one of your presentations back in the past. Just to make sure that we are on the same page. Artificial intelligence is anything you want to do to create a system or device which acts intelligent. It could also be completely rule-based. If you are very smart and you're able to do that. It's very broad. It started many years back. It had a couple of winters in which expectations were too high and then nothing happened. And of course now it's a big hype, but it's a very broad field. Machine learning is a subset of it, where you actually try to learn this behavior, these intelligent rules from data. And deep learning is a subset of machine learning, which is using a particular type of algorithms, neural networks, as I will explain in a second, to tackle those problems. So sometimes I hear people talking about AI and deep learning as if they would be one-on-one. Obviously that's not the case. AI is super broad, machine learning is a subset, and deep learning is a subset. So, looking at deep learning, the first thing that starts is the analogy with the human brain. We are by far the most sophisticated machine on the planet. I wouldn't say in the universe because we don't know yet. Probably there is something better than us if we are not too egocentric. The importance of the brain and why it works so well is the fact that it's highly parallel. So we have billions and billions of neurons and a large amount of synapses per neuron. So you can do a lot of computation, even if it doesn't go very fast. You have so many neurons and synapses that you can compute a lot every second. And the information and our knowledge is stored in the connections between the neurons, so in the strength of those synapses. The analogy in neural networks is with those artificial neurons, as I will talk about in a second, and the weights between them. And the great success of deep learning at the moment is due to the fact that you can use GPUs, which are highly parallel, where you can encode this information and process it very fast. If you look at the number of executions and operations we do per second in the brain, it's around 10 to the power of 16. It's very large. And at the moment, I think we're around 10 to the power of 13 for GPU per second. Of course, if you put it into a cloud computing farm with a lot of GPUs, you can go to something as big as a brain. But it takes a whole cloud farm to actually be able to simulate one single brain. And we haven't done that yet. So you should feel very proud of how much power you have in one hand. Very cool this. Okay, so again, this is a very simple explanation of deep learning. It's not comprehensive, but I hope you're gonna get something out of it. We have to do a step back, and I'm gonna use images all the time, but it applies also to sound, to text, to signals coming from sensors. So go through with me with images, but then it should apply also to other domains. So let's imagine you like to train an algorithm to distinguish pens from caps. In the older world, let's say around 10, 15 years ago, up to a few years back, what we would do, we would have an image data set, we would think very hard about the problem at hand, and we would construct features. So we would say, if we have to recognize faces or pens, maybe edges are very important, or contrast would be very important, or the texture of the colors. So that would be quite a lot of effort that we would have to think of, machine learning engineers. And then after we would construct features, we would apply a classifier. So if we look at a face, one of the features which is very important is normally the contrast between the eyes and the nose, or the forehead and the eyes. So you can see those patches here, those black and white patches. They are nothing more than contrast detectors, so they detect the contrast between a part of the image and the other one. And once you scan those contrast detectors on the image, you get out numbers. So you go from pixels to a vector, which has numbers. And after you compute the vector for every image, you would create a classifier and be able to classify the image as a face or a non-face. So a lot of effort would be spent on creating those features. So these are not scientific numbers, the 10%, 45, 45, but yes, you would spend some time creating a database, but most of it would be spent on thinking hard about the features and thinking hard about the classifier. That was something which worked very well. If you look at Snapchat and a lot of other applications, mobile phone cameras and other cameras, they use face detection, probably still using exactly the same algorithm I explained. Most of them don't use deep learning, and it works really well. So there's nothing wrong with it. Nowadays, though, deep learning is revolutionizing the way we tackle those problems. And I'll try to explain to you my view of why this is. So in this image here on the right, you see circles, which are neurons, and weights, which are lines. I divided them in colors. On the left-hand side, you have input neurons. Those are the ones which map to your input, being an image, text, sound, sensor inputs. Typically, you have, for every neuron, you have one particular input, or an area of the image, or a part of the sensors. Then on the right-hand side, you have the output neurons. These are the ones which map to the problems you want to solve. It could be classes, or it could be high-level representation of what you want to solve. And in between, you have these neurons. This noise. They're called hidden neurons, and they're the one which will do most of the job, the green one. So let's see how it works. By the way, the deep part of deep learning is how many layers you have in between. So if you have a lot of layers, that's why it's called deep. If you would have only one of these, one of those here in green, they would not be called deep. So the deep part of deep neural network comes from the amount of hidden layers. So let's say that we have covered images and we label them according to caps, pens, and glasses. What happens, and this is not exactly the way it works, it's a convolutional neural network, so I should actually put something where the yellow part is, but at high level, that's more or less what happens. You scan an area of the image and you extract the pixel values out of it. That is fed to the input side, and then the information is moving from left to right all the way until the end. You initialize the network with random weights, so of course you don't expect a good result. If you put in an image of pens, maybe you get out cat as an answer, because it was random, so of course there is no reason to expect it to be better. Then you use what is called backpropagation, gradient descent, to update the weights. And this is an algorithm which is trying to modify the weights, which were initialized randomly, to then get the answer that you want. So in this case, you try to modify the weights so that the next time you're going to put this image, it's going to be more likely to be pants instead of a cap. And you do this more and more times, millions of times. And at the end, what you will get out is a network which will be able to recognize images in the right way. So if you look at the effort nowadays in deep learning, most of the time you spend on actually gathering images with the right label. And then remaining time you spend actually thinking about which network to use and to train the algorithm and change the parameters. And this is very different compared to what I showed earlier, where you spend a lot of time thinking about the features. And the reason is that the network will learn the features itself. So the network itself very often is seen as a black box. That's you put something in and it comes out, and we don't really know what happens inside. But there are a few ways to actually check this out. And this is one of the papers. There are a few more recent ones where they use a method which is a little bit as if you would take an MRI scan of this artificial brain and try to see what happens inside the brain. And what you see here is different the images of what's going on in different parts of the hidden layers, from left to right. If you look at the first area here, down here you see what the network learned, and those are edges and color blobs. So very low level things. Then a little bit to the right you see texture, more to the right you see object parts, and all the way to the end it looks a bit hallucinated, but it's full objects. So what it means is that the network goes from the left, it's very low level concepts, edges, and all the way to the right is very high level semantic concepts. So you have to think, when you discuss with a human, let's say I would ask you, please tell me if this image is an image of pants. You wouldn't start telling me, oh, count the red pixels, or tell me how many edges you have. You would ask me, okay, does he have two legs? Does he have buttons and a belt buckle? So you would ask me questions which are very high level. It's not pixels, it's how many legs does he have? And that's what happens here. On the left hand side, you could ask questions to the network, does he have red pixels? In the center, you could say, does he have very long things? And on the right, you could say, does he have two legs? And this is fundamental of deep learning. The deeper it is, the more high-level semantic concepts you can ask to the network. And that's an essential element of deep learning. The higher level concepts you extract, the easier it is to discuss, between quotes, with the network and ask smarter questions. That's the fundamental part. So if you think about sensor data, you don't have to ask the question, is it changing rapidly? But you could say, is it behaving in a very expected way, or is it behaving like last day? You can compare things at a higher level, questions that human would ask. Of course, neural networks are very diverse. So I just showed you one type. They pretty much all share the fact that they have this hidden layer, so this green part. Some of them have memory, some of them not, and pretty much every week a new one comes out. So by no means what I showed you is applying and solving everything. But the main idea, you have input, you have output, you have hidden layers, and the deeper it is, the more high-level concepts you can extract. That's the end. Here I just put a few images of what, in this case, convolutional networks can do. Here is generating like galaxies, simulating volcanoes, increasing the resolution of face images, extracting the full human body pose, training a robot to be able to navigate in the room, of course self-driving cars, training the behavior of a puppet to work on rough terrain from scratch. And on the right hand side, it's a very cool application. They use Google Earth images or satellite images to automatically detect the roofs of the houses and automatically estimate how much solar power they could generate just by looking at the angle, without going to any house. So you will be able to then tell people, if you install a solar panel on your house, you can save this much per year, or you can generate this amount of money per year, without sending anybody there. This one is just a summary of what I've said. Is more if you want to look at the slides later on. The fundamental part here is that deep learning is nothing without data. So if you don't have data, deep learning doesn't really help you. And even if you get a network which someone else trained, well, someone else created the value for you. So you have to remember data is essential for deep learning. Okay. So far so good. Are you still awake? Was it clear enough? Did it help you in any way? All right. You can also say no. I'm alright with that. And I did forget to say that, of course, if you have questions you want to interrupt, please do that, so at least I can try to solve or answer your questions at time. So I put down a few myths about AI. One of them is whenever we work with companies, very often they think that they can just buy AI. They come to us and say, okay, can we buy AI, one time so that we can solve everything we have? Nowadays, that doesn't work. There's no such a thing as one AI. It's most of the time it's very specific AI, which is trained for one specific problem. Doesn't mean it doesn't work, but you cannot sell AI once and forget it. The second part is that AI is like human intelligence. It's very different. It's very useful, but it's very specific. It's not as creative as we are as human beings. Of course, this is true today. Maybe if we would have this talk again in 10 years, we would say different things, but the state of today, there's still a very big difference between AI and human intelligence. The third myth that we hear very often is the fact that someone would want to get AI and just put it in the office and AI would learn by itself. I buy APM Watson, I put it in the room, and well, after 2 weeks, it should know everything, right? It just listens to us. Well, that doesn't work. And we know if we work in AI that we have to put a lot of effort to make it work. That's still good because there are a lot of jobs which will be created, but it definitely doesn't learn on itself. In terms of application, as Jack was saying, there are an enormous set of applications. This is just live from the GPU tech conference that NVIDIA makes every 6 months. This was done around 2 weeks ago. These are applications which are GPU accelerated. The interesting thing is that the vast majority of them are not only GPU accelerated, but they are deep learning based. You see here it goes from high performance computing, internet services, transportation, medical imaging, logistics. There's pretty much no domain which is not gaining from deep learning. This is very good business for NVIDIA, of course, because they are the ones produce the majority of GPUs. But it's also very good news for us because it means that anytime you have data, you can start applying them. I have a few examples. Some of them actually are similar to what Jacques showed earlier. A few of them are about agriculture. This is something that an American startup started working on. It's called AG Voice. And it's solving a very simple problem. Normally, farmers would have to go around the fields and monitor plants, plant by plant, and find out if there is a problem with plants. And what would happen, normally they would write it down on a piece of paper, or if they're more advanced on a phone, they would take some notes, then go back and have to create a summary of what's going on in the field. And then from there, judge whether they have to take actions. And what is going on here is very simple. The person here has a microphone, so he can just walk around the field, start talking as if you would be talking to a friend, so complete natural language. He doesn't have to use special keywords or special words. And just say, oh, this plant doesn't look too good, it has some white spots, and underneath the leaf, I see some black things. And then he moves on. And the application records, of course, the GPS position. He can take a picture if he wants, and he records what he says. And automatically then he would parse all the words that he said, create a report with locations and a summary and recommendations of what should be done. Can you imagine it's very useful. You don't need to be an expert anymore of a particular crop. If you just have a good eye to see the details, you could just walk around, gather everything, and then someone else remotely could give you an advice. And this is nothing more than pretty much a microphone and a phone. Very, very useful. This requires a bit more. This is done with drones. And they put a multispectral image, multispectral camera on the drone, sometimes a LiDAR or a 3D camera, not 3D camera, not a LiDAR or 3D acquisition. And what they want to do is estimate the yield of a crop. So they want to find out how much a crop is going to produce in terms of vegetables or whatever the crop is producing. And what they do, they fly the drone on top of the field multiple times, 1 time per week normally, and they compare the images, and because they have multispectral imaging, then they can classify every pixel in the image, whether it is a plant or it's ground or something else. And from there, they can estimate how fast the plants are growing, and then estimate how much the yield is. Of course, this allows you to plan ahead. How many trucks do you need to pick up things? How many men do you need to go in the fields to work? Obviously, this requires a drone, so it's not as easy as the previous one, which was just a smartphone, but it can be very useful as well. This third one is required a little bit more. It's a robot which is going around the fields, and it has a multispectral camera and also a little arm which can go around and measure plant by plant the size and the growth of the plants. And normally it's used to, if the farmer wants to try different type of seeds and crops in the same field, and would like to monitor how well they're performing, instead of having to send a person to measure all this, you could have a robot which does it very accurately. Of course, this is more expensive, but it is so precise that allows you to test on a smaller scale. Instead of using a lot of fields, you could use one field and measure very accurately. This one is from Blue River Technologies. That's a company in the US. I found it very interesting because, you know, normally if you want to put herbicide, either you just spray it on the whole field, or you call in a plane which flies on top and sprays on the whole field, which means you have to put a lot of herbicide, and which also means as humans we eat a lot of pesticide because it's just sprayed everywhere. So what those people thought of, it's very simple. They put a camera underneath the arms of this tractor, and the camera is analyzing the feeds that it sees, and it's recognizing which plants should receive pesticide and which plants not. And then they have different noselets underneath, which can spray pesticide selectively. So we detect the plants, which the red one here, which should receive pesticide, and they spray it on top. So they're able to actually spray 90% fewer pesticide or herbicides, which is great in terms of money saving, but it's also good for our health. And this is a beginning, of course. You can imagine you could actually spray nutrients or water them in a particular way. I find this really interesting. This is the final one I have in agriculture. Obviously, you have self-driving cars which are coming, and they also have self-driving tractors. It's an easier problem actually than cars. The idea is that because you have GPS, you can define much easier where the crop is, and normally you don't have cars and people walking around. You don't have traffic lights. You don't have kids running in between, or you should not. Of course, they can detect things in front, so they will stop if a kid will run in front of the tractor. And the idea here is that they use it 24/7. Obviously, you have to imagine in the US they're going towards a situation where you have one farmer and 10,000 acres of land. It's a very particular domain, but that's upcoming as well. The interesting thing about agriculture is also the fact that I think Jacques was showing the slide of the sensor, the precision agriculture. The number of IoT, so the Internet of Things devices, which are being shipped in agriculture is growing rapidly. That's the picture on the left. On the right, you see the estimated amount of data generated per farm growing all the way to 2034. And you see it's growing much more than linearly, which means that there's going to be a tremendous amount of data that we can use to help farmers produce better, estimate crop better, select the type of seeds better. It also means you're going to need more and more machine learning people to help that. And but it also means that a farmer working right here could leverage the software developed somewhere else in the world. Or if you develop it here in South Africa, you can sell it to someone else in another part of Africa. Because if the sensors are the same, you don't need to be there to leverage it. So there's a huge potential to use this data. Going to healthcare, this is again similar to what Jacques was showing. I don't think it's the same article though, but the idea is very much the same. So the issue is that they found out, particularly in Africa, there are more microscopes than there are pathologists. So very often you have a microscope there, but there's nobody who can actually understand the images of the microscope itself. So what those people developed is a 3D printed solution where it's simply a piece of plastic which you can attach to the microscope, where you can put your phone in, and then the phone of course has a camera and has an internet connection. And I don't think the algorithm runs on the smartphone, or maybe it does. Well, either the image is sent to a centralized location or the image is analyzed on the smartphone. They use a convolutional neural net to identify where the cells are, and obviously it goes much faster than doing it by hand, by eye. Especially if you're not a pathologist, it will take you days. If you're a pathologist, you're much faster, but they're not enough. And the interesting thing is that, of course, the image can be sent to the hospital, where pathology will only receive the images which the algorithm thought of there is malaria or tuberculosis. So a doctor can still confirm it, but instead of having to look at 1,000 images, you have to look at 10 images. And you can help thousands of patients instead of only one. And you don't have to move from hospital. So really, really nice innovation. This is something that Google did, is detecting cancer metastasis. And this is hyperspectral imaging with also the same, of course, it's very high resolution. They're called gigapixel pathology images. And literally gigapixel means that there are billions of pixels. So if you're a pathologist, it takes you a lot of hours to look at one scan. It's not a very nice job. And what they managed to do is eventually have something which is much faster than human, of course, and at the same time more accurate. And again, a human then is asked to confirm the case. Yeah, it shows again that if you have enough data, you can achieve very, very good results. This is something we are working on in the Netherlands, and it's about thrombosis location. So whenever someone has a stroke, if you have a blood clot in an artery of the brain, your brain starts dying because there is no oxygen going through after that clot. And it's very important to detect that very fast so that you can send the person to the right hospital. Depending on how big the clot is, there are different techniques. Sometimes you can send a catheter in the body and remove the clot, and other times you have to use blood thinners. And depending on the size and the location, you can send a person to a different location. And you have to do it very fast. And here we also use deep neural networks to identify the space within minutes. This is something about mining. It's a company called Mobius. And what they develop is a little bit, they call it the Fitbit of industrial machinery. It's pretty much a device, much bigger than a wrist Fitbit band, that they attach to machines, and it's able to remain functional in environments which are very moist and very hot, typical of this industrial situation. In this case, it's a mining pump, and what they check is the vibration, the humidity, the sound level, the temperature, and they give warning signs whether a machine is going to break or should be repaired. And of course, if you do that, instead of waiting until it shuts down and maybe destroys part of the other equipment, you can ahead of time turn it off, repair it, or substitute it, and then continue working. And very often you have multiple machines, so you might be able to turn off one machine and continue with production. And of course, this is very good business for the mining industry, but it's also good business for the companies selling you pumps, because they can come at the right time. This is another application in mining. I don't know if anybody is familiar with the mineral froth. You are, evidently. Anybody else? It's basically a process where you use different type of liquids, and you throw in a mineral in the liquid and you create bubbles. And depending on the chemical properties of the mineral and the size of the bubbles, the minerals will be attached to different bubbles. And you can use that to separate the minerals, the different type of minerals. And here, what is important is being able to detect and accurately count the number of the bubbles that you have. And normally it will be done by human beings. And of course, machine learning is coming in there. This particular example was from 2016, and it's still using, I say still, as if it would be bad. There's nothing bad about it, but it's using sport vector machine. I'm sure that someone is using deep learning as well. But this was very successful with SVM. Okay, so far with the examples, any questions?
I just want to quickly make a comment on that. There's actually a company called Stone Through Mining in South Africa that's doing that kind of stuff. But my first company, Seating Systems, we built we call it Froth Master, a solution that was sold to Outokumpu, Finland, that actually used all this traditional image interpretation and cameras and stuff. They're going to do exactly all of that. We implement it worldwide. But the interesting thing now with deep learning and stuff, the next generation of that, Stone Through Mining is actually doing this now, using deep learning. So it's an African-based company doing this. Cool example.
Yeah, as I said, I was sure the sound was really good. Yeah. That's great that you can confirm. I mean, it's very difficult not to find deep learning somewhere. Yeah, that's good. Any question on the previous examples, or you need a break? No. Okay. Good. Anybody of you familiar with Lean Startup?
Greece.
Okay, no. So, well, Lean Startup is actually, I would recommend to look it up. You don't have to get the book, but you can just look at a blog. It's something that Eric Ries developed from US, and it's the idea of trying to avoid spending a lot of time and money creating a problem, creating a product that nobody wants. It can be within a company or it can be for consumers. If you think about the normal development process of a product, someone has an idea in the business, says, okay, I have this vision of this product, I need all those features, I need 1 million, they will take 20 people, they will develop it for 2 years, they put it on the market, and then it doesn't sell. Now you spend all this money, all these people, all this time, and eventually you find out that it was actually not worth the effort. So the idea here is to use this, they're called loops of build, measure, and learn, where you try to divide and break down your problem and your product in smaller hypotheses. So if you say, I want to develop a new machine to help the mineral froth separation in a faster way, and I think the new machine should be 10 times as fast or 10 times as accurate. That's what you think, but you have no way to prove it. So maybe you should first go out and start interviews with all the people which are using it and check whether what you have in mind actually makes sense. And then maybe you think that it should be the machine should be smaller, or it should be cheaper. Then you could start testing these ideas that you have. Because if you spend 1 year developing a cheaper machine, but in reality the problem was not that it was expensive, but it was that it was not accurate enough, you should put your effort in making more accurate, not cheaper. So if you look online, you have a very, very good example applied to pretty much any field, but it's trying to avoid the effect of creating a product in isolation without confronting it with the actual user, and testing your hypothesis as quickly as possible and as early as possible. Now in machine learning, one of the issues that we see most of the time is that you go to a company and they would like to have a problem solved, and they say, now we're using humans, or we're not accurate enough, we need to make it faster, cheaper, more accurate, depending on the case. But whenever you develop the solution for them, this result will not happen on day one. It might take you months to go from the idea to the realization, maybe even 1 year, to gather enough data and train your model and find the right models. So what can you do about it? What happens today is that a research company goes, or if you have your internal research in a company, depending on how you're set up, you would say, we need 1 year to develop it. You go in your labs for 1 year, and then after 1 year you get back and say, now we have a solution. And in the meantime, nothing happens. And what we try to do is instead doing it in steps. So when you start a model, very often you have very low accuracy. It doesn't need to be 30%, this is a very generic example, but can be much less than what you would actually need in the final application. At that time, normally you would say, well, it's too low, so we cannot show anything, we'll wait until it's done. But in reality, you could already start discussing, if you have a big company, with all the business stakeholders, which would actually have to then put this idea in production. And also check whether internally the company would have to change anything if you use a machine. So if now you're using people, but later you need a machine, you might need to create data flows which go through the organization, or create reporting, or have someone who's responsible to look at the data. So you could already think ahead of all the changes that the organization would need if you would use machine learning. Over time, you would start having a better accuracy. You might need to gather more data, so you might need to have someone which is responsible to gather more data. And in the meantime, you can start refining the hypothesis you made in your business. So what was needed for your business? We saw that we had to modify this and that, so you might start hiring people, or creating new spaces, data flows, or what else. Once you get a little bit higher, you might be able to start applying it already in some small pilots, knowing that the accuracy is not high enough, but at least people get used to the feeling that the machine is doing it. That's very important, because if you don't do it in advance, whenever you deploy it, some people might complain, they might not be happy that you're using a machine instead of people. So if you start doing it in advance, you're going to have less problems. And at the end, finally, you will be able to start using the application in your business. And this is what normally happens. People start at the end. They wait 2 years, and then they apply it. And then they figure out that there were a lot of other things that, next to the algorithm, should have been fixed. And if you start from the beginning, by the time the algorithm works, you're actually ready to use it. So this is very high level. It's difficult, of course, to explain it for your particular business, because everybody of you works in a different domain. But I hope it can help a little bit to think ahead. Don't wait until you're done to try to implement it in your business. Start from the beginning to discuss with people and say, we're going to use machine learning to do that. What do we need to change to make it real? And in the meantime, develop the algorithms. I hope this gives you an idea of what to do with it. If you have questions about it, you can also come later and we can have a chat maybe about your specific domain. This is what I said pretty much. Most of the successful cases in AI are about narrow AI, specialized, not general. And one of the most important point is to plan in advance whenever you want to apply. The last slide I showed. Okay, you're still with me?
Yeah.
Right. this is to show you with data, to show you actually what I said earlier, but a little bit more quantitatively, how important data is. In 2001, at Microsoft, a couple of researchers asked this question, does it make sense to invest in building more and more complex algorithms? At that time, there was no deep learning. There were neural networks, but deep learning was not there yet. And at that time, people were spending a lot of effort in developing better and better algorithms. And what you see here, it's on the horizontal axis, you see the millions of words in a data set. And here on the vertical, you see the performance. The red line is, this was a task about classification of text documents according to a certain set of classes. The red algorithm was the state of the art at that point. It was memory-based. And the typical data set was using around 100,000 words, or maybe around 300,000. And indeed, the best algorithm was the best. Yeah, that's why it was called the best algorithm. And the simplest one was performing much worse. And the researchers were spending a lot of time developing better and better algorithms. And what people at Microsoft found out is that if you go from 100,000 words to 1 million words, 10 million, 100 million, or 1 billion words, so you increase it to 10,000 times the normal size, you see that all of a sudden you go from the best performing algorithm being the most complicated one to the situation where the best performing algorithm is the simplest one. So you can have a very simple algorithm, but a lot of data, and then your situation is reversed. So people at Microsoft figure out, well, we better invest in data instead of algorithms. And that now, of course, neural networks advanced a lot, and there's still a lot of very sophisticated networks which are coming out every month. It doesn't mean we should stop research on algorithms, but it just means that data is fundamental. You can have the best algorithm in the world, but if you don't have enough data, you're going to lose. In 2017, so this year, some researchers went back to find out whether this was still the case. And they saw was, in this case, it's a case about images, millions of images. So of course, we're using much more data nowadays. They started at 10 million, and they went all the way to 300 million, so 30 times more. They're using a deep neural network. Well, the line here is this is with transfer learning, and this is not, but it doesn't really matter. They both go up, and you see that if you increase it 30 times, the accuracy goes up quite a lot. So there is no sign of saturation, even if you go from 10 million images, which is huge, to 300 million. This tells you keep getting data. That's fundamental. Data is key. What is interesting is also the fact that if you look at the GPU power, that's going up every year. If you look at the model size, this is the architecture of a deep neural network. So how many neurons, how many layers the network has. The higher the number of layers, the more powerful the network is. Remember that I showed you beginning the image where I said at the left you have edges and at the right you have high-level semantic concepts at the very beginning? The more semantic they are, the more high-level conversations you can have with the model. So the deeper the level, the higher, the bigger the size, the more high-level conversations you can have, so the more powerful it is. So this is going up. Every year we have better models. But the data set, the publicly available data sets that universities put out, very often is constant. It's not exactly constant, you see some spikes, but it's not growing as fast. So we have better models, we have better GPU, but we don't have publicly available more data. Companies have data as well. That's very important. So it's no wonder that also Microsoft is here, even if it was playing catch up. If you look at Google, Facebook, Amazon, Microsoft, I should also add Baidu, Alibaba, and WeChat, and a lot of other companies, most of them offer free products. So free email, free image storage, free maps, free video storage, social media channel, messages. Well, in this case, shopping search is not free. Well, you can search for free, but you cannot get the products for free. And Microsoft free search as well. It's great because it's all free. But of course, in reality, they are gathering data to then train models, right? So they knew in advance. In 2001, they already knew data is important. 17 or 16 years later, they have been gathering data all the time. And no wonder these are among the biggest companies in the world because they gather a lot of data. And we help them to annotate it for them. This is a nice service we provide. Now, there's a good news to it. If you look at the amount of data which is being generated in the world, well, this was last year, 2016, and going ahead in the next 8 years, it's very difficult to estimate, of course. Nobody knows exactly how much data is generated on the planet, but this is a trend. We will go to from around 16 zettabytes. These are trillion gigabytes. It's easier to understand. So it's 1,000 billions times 160. So starting from 16, we will go to around 160. So it's a huge amount of data, whatever number you put there. Very, very big. What is interesting is that nowadays, most of the data comes from consumers. So if you think about Facebook, Instagram, YouTube, they're all things that we as consumers produce. But going in the future, around 60% of data will come from enterprises. And the reason is Internet of Things. So all the machines, all the sensors that will be installed will be generating eventually more data than consumer data. Which means that there are going to be a lot of companies which will have a tremendous amount of data. And as I've shown already, data is value. So there's a lot of value to be extracted if you know how to extract it. So I think it's very good news. This is a very blurry image, but I like it a lot. It's an image from a TechCrunch article, and they were looking at startups which had at the core artificial intelligence, and they were asking the question of how resilient to competitors those companies would be. So how easy would they be put out of market by a competitor? And these are different modes. So protection layers of a startup. So your startup is encapsulated in the center. And the most important part is number one, so the strongest protection is proprietary data. Then you have domain expertise, and you have workflow position and customer value, but they're more fuzzy. But proprietary data is fundamental. So again, the best way to make your AI company successful is to have proprietary data. And well, we know there's going to be a lot of data generated. And this is basically the summary of what I've said. It's good news because there's more and more data generated. Data is the way that deep learning works. The best way to protect your company is to have proprietary data. So overall, make sure you find a domain or a company which has a lot of data and you use it to create models. That's the short one. Are we okay so far?
Yep.
Still awake? Okay. Well, I hope it's not too long, by the way, for you. So,
no, that's right. We'll do a break right after you.
Okay. I have here a few slides to follow, and I could skip through some of them pretty fast, but the idea is, of course, as I said, data is fundamental, more and more data will be generated, but I wanted to give you some examples of how to gather data or enrich data. And again, all those examples are related to images, but they are applicable to our domains. You have to be creative, but they are. Well, so first off, it's a no-brainer, but it's important to mention because very often people start working on the problem and they forget about this one. There's a tremendous amount of data which is available publicly. I'm sure that in Africa there are also databases available, but there's some in Europe, some in the US, in China probably they are, but it's difficult for me to find them because I don't understand Chinese, so it's more difficult to find them out, but they are for sure. And these are 48,000 different data sets. So they're not 48,000 data points, they're 48,000 data sets, or 197,000 data sets. Each of them might have millions of data points. And what is essential is that if you know what transfer learning is, are you familiar? You are. I'm going to stop asking to you. If you know what transfer learning is, which is that technique which allows you to take a pre-trained neural network model and then update to another domain, update the weights. Well, we can talk about it later if you don't know what it is, or you can Google it. It's anyway, it's a very, very good trick that deep learning has. You can transfer from one domain knowledge to the other one if it's close enough. Which means that instead of starting from scratch, you could very well look at one of the data sets available, learn from that, and then transfer to your domain. Now, proprietary data is really important, of course. That's what I mentioned earlier. 60% of the data will come from proprietary data from companies. If we look at examples here of agriculture, as I mentioned, mining industry in general, healthcare, and B2C, so anything that you can get from websites or mobile apps, it's fundamental to remember that there is no such a thing as data in general. It can be structured or unstructured. So structured data is whenever you capture it already in databases, so we can already say this particular input is belonging to this type of feature. Unstructured is typically images and text or videos. They're just images, but there is nothing else known about them. And then you have obviously labeled and unlabeled data. Very often we work with companies which say, oh, data, no problem. We have a lot. We have been gathering for 10 years. And then we asked them to show to us their data, and well, it's fully unstructured, it's not labeled. That's a mess. You know, and if they would have asked us earlier, check with us how to gather data, we would have helped them to gather it better. So it's important, if you start gathering data, think ahead which kind of application you have in mind and plan it. Now, scraping. In this example, I'll show you a little bit what we have done. Maybe it's very specific, but stop me if you find it too specific. But maybe it gives you a little bit of an idea of what you can do. Do you know what scraping is, by the way? Okay, so in this case, we built a product which is able to classify any product given a text description and or an image towards the categories of Amazon, eBay, or a large marketplace. So imagine you want to upload 10,000 articles to Amazon. Normally you have to manually select the category to which it belongs and put all the attributes, and we created a system which does that automatically. So we started by scraping a lot of websites. We ended up with, well, nowadays it's actually much more, but let's say 20 million products scraped from the internet. And the first step we had to do was very painful, but we had to start somewhere. So we started automatically filtering with keywords from the text, all the objects, the item we found. We clustered them visually, and we had to have someone manually confirm it. But eventually we ended up with 500 classes and around at least 1,000 images per class. This process was around 2 weeks, so it was pretty painful, but from 20 million images we ended up with a lot of label data. And of course, the better the website you start from, the easier this process is, because the labels you get from the website are really meaningful. Then we used, we trained a deep neural network, of course, as I explained earlier. And this part is a bit more technical, but in case anybody of you is actually familiar with neural networks, that's a very nice trick, and I just wanted to put it up here. Again, what I said earlier, at the left-hand side of the network you have very low-level features, not very semantically interesting features, and on the right-hand side they're higher level, so you can have a more interesting conversation about what things are. So if you take this dress and you look at the rightmost set of neurons and you get the values out, you have an abstract description. So you would talk about folds and the fact that it looks dressy or it looks like clothing compared to it has red pixels. So what you can do, if you take out, imagine you have these 3 bracelets and you want to compare them. If you compare the pixels, well, here you would say these are darker pixels, these are lighter pixels, but it's not a very interesting conversation. That's not the way you talk with a friend about a bracelet. How many dark pixels does he have? You say, is it leather-based? Does he have jewelry? Is it thick or is it thin? As a more traditional modern style. So you can actually compute the distance in this vector space. So you try to look at the distance in the high-level semantic space. So it's really, you discuss about high-level features. In another way, you look at this picture and saying hot air balloons are more similar to each other in this space than they are to cats and dogs. Because evidently there are different types of objects. And it doesn't matter if this has red pixels and this might have brown red pixels. Semantically they're different. But if you look at red pixels only, they might be very close to each other. So if you take a red cat, it might be closer to this one than a green hot air balloon. So let's take, we took all the bracelets we had, and now we can take one bracelet and find all the bracelets which are similar to each other in that space. So all of a sudden you find bracelets which they're very thin, they're typically made of metal, so it's like a human would tell you, if I give you this bracelet, show me similar bracelets. It's not the image itself, it's a bit more than just the image. You can do the same for this kind of bracelets. Same thing for shoes, these are all random shoes. You take these shoes, you get sneakers. You take these shoes and you get, these have more stripes and they're more sporty, and this is slightly less sporty. And this helped us to go and refine a number of categories. And we added around 250 more. So this approach really helps to clean the data. Again, it's a bit more technical, but it helps you to go from scraping a lot of data to refine it. And then what happens, this is the application that we have, you can put in an object and it will categorize it, gives you colors, and then give you additional text. And that's something that you can pretty much get starting from scraping data, refining it, using some tricks, in this case embedding spaces, and actually getting a whole protocol. Still with me?
I've got a question.
Yeah. Yes, one question.
So I was just waiting for this moment. So traditionally, if you have to make a classifier, then you could add, say you want to add in some other description that the user put in, you scrape this data, there's the image that you're using for deep learning.
Yeah.
Let's say there's a description which said and bag, how would you, with traditional classifiers, you add that in as another feature. How would you add that into a deep learning system?
So how would you use, the question is how would you use text, metadata text from the website?
Yeah, so you're combining different kinds of data, not just images.
Right.
So the image is your main input, but you want to combine other data too.
It's very interesting. Yes, you can do that. So first of all, you normally don't feed in the whole sentence as it is. You have to convert the sentence into numbers, because these networks that you see, they like numbers to be fed in. So normally what happens is it's kind of called vectorization. So you have to convert every single word into a unique number. So if you have dog, every time you see dog, it will be converted to number 1013, and every time you see bag, it will be converted to another number. So first you take all your vocabulary, so all the words you will ever find, convert them all to numbers, and then you have to pretty much create a representation of vector representation of that, either the numbers as they are, or you can do a smarter step where those numbers are compacted a little bit, so you don't just get a million numbers, but it can be a shorter vector, and that vector can be added to. So if you put it here, so this would be the input of the image, right? So you could also extend it, and over here, add more inputs where you fit in your text representation, which is a vector again, and then expand the network. Of course, this is very high level. This is a convolutional neural network, and over here, if it's text-based, it would not be convolutional. But you can add it over here and then merge it a bit later. There are a lot of examples on the internet where you can see combination of text and images, and they're all a little bit different. But eventually, first you vectorize your text into numbers, and then you can compress that numbers with vector space, and then you will add it to your network at some point. So it is totally possible. Is it something you can do in 5 minutes? Not, but you can find models which allow to fit in images and text.
Yeah, I think yesterday we showed an example, specifically we talked about convolutional neural nets and recurrent neural networks. We feed in text, we generate, for instance, captions for a picture. That's another example of where you actually combine.
Indeed, yeah, they have very interesting examples where you can also, the embedding that I showed you earlier, you can create it from images and text, and indeed you can fit in an image and get out of a text, or you can fit in text and generate an image out of the text.
I guess this gets quite interesting when you do video analysis. For example, you could classify the dog as barking.
Yep.
So you're then fusing visual and audible signals.
Yeah, indeed. Also, as I said, this of course, this is not a lecture of 2 days, but the network you see there is, I just put those color circles in yellow and say you put the image inside, but indeed, any sensor data, any audio data, you can fit it in, and then depending on the domain, for images you use a convolutional neural network, for text you have to pre-vectorize it, for sound you might want to go to the frequency domain, for sensors it's time series, so you might first want to convolve it with and get out some first, second order, or third order approximation. It really depends on the data you have, but once you have numbers out of it and you represent it as a vector, you can pretty much feed it in every network. And then the recurring part is if you want to have memory inside it. You want your network to behave differently over time. But, any other question? Right. Data augmentation, again, this is for images, but it can work for other things. In this case, we wanted to recognize the logo, so the company which was sending an envelope from scans of post. And what we started from is simply downloading a lot of logos from internet, and we knew the company corresponding to each logo because we scraped it from a certain website. And here it's actually a very simple application, but it really works. So I just wanted to show it to you. You can make things work very simply. You start from a single logo. You know how a logo would appear in an image. In this case, the particular postal company we were working with was binarizing the images and creating look at edges only. So you can convert this image in color to a binary edged image, and then you know that you have some deformation on the paper. You might have some water stains, and but pretty much that's it. It's not a 3D image, it's always flat. So you can already, you know pretty much all the deformations that you expect a piece of paper to have. And you can literally write them down in code. And when you do that, you can generate from a single image a lot of variations. You can do that for all the logos. And then you create a system where you start from logos, you augment them, you train a classifier, you look at how well it performs, and then if it doesn't perform well, or for a particular logo it doesn't perform well, you go back to your augmentation algorithm that you wrote. There's no AI in that part. You really literally wrote the rules, and you say, well, it seems like this logo is not detected well. It looks like the one we find in the actual real example on the postal images. They look more different. Oh, maybe this deformation we didn't use, so we also needed water stains. We never thought about it, so let's simulate water stains. Then you train it again, and it works better. And this works with images, but again, you can also simulate and augment text. So you could augment spelling mistakes, or if you have sensor data and you know your sensor is noisy, and sometimes you have peaks in the sensor, you can simulate that as well. If you need to be very much aware of the domain you're working with and understand your data, but you can simulate a lot of augmentation, which really helps. For images, you always have to do that, by the way. Okay, generation, this is a bit more funky, but it's a really, really hot area. Anybody of you has heard of generative adversarial networks, or GANs? Yeah, I see other hands, that's great. Yeah, they're a really cool topic. It's not fully understood yet in the sense that, well, there's a lot of articles, a lot of math behind it, but it's very difficult to control them. But in a nutshell, what they do, you train two separate networks, a generator and a discriminator. And eventually what you want to do is, let's say that you want to generate dresses, images of dresses. And again, this is for images, but you can apply to other domains. So the generator, both networks start from zero. So the generator has to generate images which look like dresses, and the discriminator has to take the image as the generator generated and say, I think it's a real image, or I think it's a fake image. So this is the thief, and that's the policeman or the detective. And what happens is that you train them one after each other, and they get better and better. So initially the generator might do an image which looks like noise, and the discriminator might give you a random answer. He has no clue whether it's a real or fake. If you look from, we did for t-shirts and shirt dresses, we did for shoes and a lot of other things. Here it's where you start from after a few iterations. It doesn't really look like a shirt, a dress, and a t-shirt. And you see that over time you start getting patterns. They're not perfect, but you get a lot of variations, which is very interesting. And the interesting thing of this is that you do need to feed examples of t-shirts to the discriminator and to the generator to start training it, but then it goes on by itself. And you get out things that we could not come up with. So while in the previous example, the augmentation, you are the expert of the domain and you think about water stains and rotation and deformations. In this case, it's difficult to write down in rules how a t-shirt should look. You know it has two arms and short sleeves, but in the center, you don't really know what to put. And in this case, the algorithm comes out by itself with suggestions, so it's more creative than what you could be, or it's not more creative than yourself, but it's in a faster way, creating more variation than what you could think of. So this is used whenever, as I put down here, whenever the variety of the data that you expect to have is much larger than what you can come up with in rules. Or if you would have to do it in rules, it would take you a long time. By the way, if you generate t-shirts, the objection to this would be, why don't you just download random images from internet and paste them in the center of the t-shirt? That's also a very good algorithm, and it could very well be that you can use it, but that doesn't apply for everything. For shoes, you cannot paste images on top of the shoe. You have to look at different type of materials. So you have to be smart and not be blinded by this. If you find a faster way, just use that. But sometimes you cannot find it, and you get really nice results. And then there's the last one. It's data simulation. It's one step further. So if you look from here, you take data which is existing, you look at your own data, you scrape it from internet, meaning someone else had it. You do simple augmentation, you do more funky generation, and then the last one, you don't even have real data, you simulate it from scratch. I give you here two examples where you can find some information about it. One is the OpenAI universe. You are familiar with OpenAI? So OpenAI is a non-profit organization that Elon Musk created, the guy from SpaceX and Tesla and Hyperloop, because he's very afraid that AI will take over the world if you don't do something about it. So this case here, it's actually a very nice program. It's pretty much allowing to take any video game or anything which is controlled by a mouse and a keyboard, and the network will, they create an infrastructure around it so that you can just feed that to a deep neural network, where the network will control the keyboard and the mouse, and it will be fed the pixels that it sees on the screen, so you can train it to learn games. But the nice thing with the OpenMind one is that you can feed any video game you have, and the framework allows you to just load the game and it will start learning. And which means you could even put in PowerPoint, and I have a network learn how to do PowerPoint. It's very generic. You don't have to change PowerPoint, you just plug in the framework, put in PowerPoint, and it will start learning. And it's crazy what you can do with it. And DeepMind did a lot of very good things as well. More pragmatically, on the left-hand side you see the simulation of a drone from Microsoft. So it's a whole environment, it's called AirSim drone simulator, which is basically simulating what a drone would see flying around. And on the right-hand side is the Deep Drive universe. It's basically using Grand Theft Auto, so GTA, the video game. And Grand Theft Auto is a very sophisticated video game. It's, I think, I don't know how many 10,000 of developer time was put to develop the game. So it's super realistic, a lot of different scenarios and environments, a lot of effects of smoke, accidents, night and day, and fog and rain. So as a researcher, if you would have to manually program all this, it would take you 10,000 years, because there use so many people to do that. Now you can just take a video game which was developed to play games and train your network to learn how to drive, which is crazy, because you can just take advantage of something. And it's fully legal, by the way, so it's not that you are doing something illegal, but I find it amazing. And one other example I don't have on these slides is about robotics. So if you want to train a robot arm to pick up something, there's a whole simulated environment where you can load your robot and have it interact with objects, and pretty much a lot of examples shown that you can train your robot fully in virtual reality, not even virtual reality, in a virtual environment. The robot will train there, and then you can literally take the same robot with what you learned on the virtual environment, transfer it in reality, and with few adjustments, it will just do the same again. And it's crazy because you can go much faster and you don't have to damage anything. And that's what I wrote down here as well. When do you do this is whenever you could gather training data, but it would be very dangerous to do it in real life. So imagine you would just take an algorithm and let it drive a car around the city. Well, you might kill people, that's not very good. Same thing with drones. And maybe robots in a production chain is not very dangerous, but it's expensive because you will break that thing, so it will take a long time. So in this case, simulations would be very useful. And the interesting thing here is that with graphics becoming better and better every year, you see video games, sooner or later they will become indistinguishable from reality. So if you can use any video game to train anything, well then you can start imagining that you have almost no limits to what you can learn. So it's very interesting to think about all the possibilities. As I said earlier, all those examples were about images, but it's very important you don't get out of my presentation thinking it's only images and well, that's a pity because I work with gas sensors. You can augment data from sensors, you can do things with genomics, audio, text. Pretty much everything I said in one way or another applies to it. So you just have to think about the keywords I mentioned, and you look at generative adversarial network and do it for text and pretty much augmentation of sensor data. It's all there. So just broaden it up. I mentioned images because it's easier and looks prettier on pictures on the slides, but that's what I said. And then the last slide, so you're done finally. I put down some questions that we normally ask companies working with us. So it really depends which business you're working on, of course. But the first one is, do you have a target application in mind? A lot of companies come in and say, we want to work with AI. That's it. But yeah, they have no clue what they want to solve, so you have to know exactly what you want to solve. It sounds funny, but there are people which really reason like that. The second one is, do you need a lot of training data? Do you need label data or unlabeled data? I haven't touched upon the whole thing on unsupervised learning. It's a very big domain, so sometimes you can do things with unlabeled data, but you need to be aware that you can do it, so you need to plan ahead. You have the data, can you acquire it, or how long will it take to collect it? And if you need to collect it, are you collecting it the right way? So as I said earlier, if you know you want to use AI, don't start collecting data first for 2 years and then start developing the algorithm from day one, even if you don't have enough data. Download it from a database, generate it, buy somewhere else, but try to develop earlier. and as I showed you at the beginning, try to incorporate it in your business early on and update your business before you get to the end. So that's it. I hope I didn't tire you with this. If you have any questions afterwards, I'll be very happy to discuss with you. I'll be here until Sunday, but I think I will not be here specifically until Sunday. Thank you very much.
Thank you. Okay.
Any questions for Tommaso? There were some good questions initially. Yep.
For the part where you were refining your categories in your model, was that because you, for example, knew you were trying to categorize shirts and shoes, but you didn't know how many different kinds of shirts or shoes you had? So then you put them through the model to some sort of clustering at the end and find how close, how many clusters you could get. Yeah,
that's a very good question. Indeed, we knew at high level the areas that we wanted to explore, so that specifically was clothing for that application. And but indeed, sometimes you're not aware of the distribution of your data ahead of time. So we didn't know indeed how many types of shoes you had, exactly as you said. So what we did is we had the high level separation, and then we actually went in with this trick of the embedding, and we then used clustering in this embedding, and we actually checked whether the proposed clusters had a meaning for humans. And we just had a visual interface which would say, look, I found this cluster. Is that something which is a separate category? If so, label it. If not, we leave it as it is. And yeah, that's very useful. The trick there is indeed using this embedding space. So do the clustering not at pixel level, but at higher semantic level. So that indeed, if you do the clustering at pixel and you do it at the embedding, you clearly see that the one at the pixel, the clusters you get don't make any sense. When you do it at the embedding space, they make much more sense. Not always, but very often.
Okay, great stuff. Thanks a lot. We can definitely talk a lot more. I can see you've got a lot of practical experience. It's 11:15, so what we're going to do now is definitely take a break. And let's start at 11, because we've got Owens here. Great to see you here. That's another guy that was at deep learning in Dava. He's also very knowledgeable on deep learning and stuff, so looking forward to your presentation. And then, yeah, we've got a few other presentations after that. Okay, so 15 minutes, 11 o'clock. Thanks.